Beneath the surface of the world, beneath the shadow of Geneva, is a marvel of human ingenuity and a possible sign of destruction: the monstrous Hadron Collider, LHC. Experts may now concentrate on subatomic particles and discover the mysterious God molecule, the Higgs boson, thanks to this machine, an unprecedented tool. Renowned physicist Brian Cox has provided a disturbing explanation that has caused scientists to feel conflicted, enabling them to examine the real surface of space-time and test the basic components of matter. However, these impacts enormous energy also pose serious risks, both known and unknown. The potential production of several black holes or other unusual phenomena that could have unanticipated consequences is one of the most urgent worries regarding the operation of the massive Hadron Collider. The chance to unintentionally produce horrors that are out of our reach is nevertheless disruptive, even though theoretical models indicate that any such black holes would be temporary and pose little threat to Earth or its population. Furthermore, in order to reduce potential risks, the collider's extensive safety procedures and supervision are necessary because of the test's immense scope and complexity. The international community of scientists and researchers involved in the collider's operation is well aware of the need of putting safety first and making sure that every test is carried out with the highest care and responsibility. In addition to being a marvel of modern engineering, the Large Hadron Collider is a key hub of particle physics and cosmology today, having the ability to astound and challenge our knowledge of the fabric of reality. It has significant ramifications for our understanding of existence and is primarily focused on testing the fundamental particles that comprise the universe. By simulating conditions immediately following the Big Bang, the LHC offers researchers a unique chance to investigate the Higgs boson and other fundamental particles. In 1964, Peter Higgs and others proposed the Higgs boson, also known as the God particle, as a crucial component of the standard model of particle physics. The basic forces and particles that comprise the universe are described by this model. The Higgs field, an unseen force that gives other particles mass, was shown to exist in 2012 with the discovery of the Higgs boson at the LHC. This finding was a major achievement that confirmed decades of theoretical research and expanded our knowledge of the hidden structure of the universe. But like any significant scientific undertaking, the search for knowledge at the LHC is not without its possible dangers and ethical conundrums. Because particle collisions at the LHC involve such high energies, it is impossible to completely rule out the possibility of producing new kinds of matter or starting unexpected processes. Concerns regarding the possible repercussions of such events have been raised by certain scientists' conjectures regarding scenarios in which high-energy collisions could produce tiny black holes or other strange particles. Even though the majority of specialists believe that these hazards are quite remote, scientific research is inherently risky. The enormous significance and possible risks of this research are highlighted by Brian Cox's confirmation, which highlights the possibility of replicating a small Big Bang inside the LHC. The Large Hadron Collider is the apex of contemporary science, yet its remarkable capabilities also raise important questions regarding the boundaries and obligations of scientific research. Although the collider works at the limits of human understanding and technological capacity, its design and operation attempt to provide answers to basic concerns about the cosmos. The nature of scientific risk and the moral ramifications of such cutting-edge research are important issues that are brought up by this intersection. Replicating conditions just after the Big Bang is one of the most exciting features of the LHC, providing a fascinating window into the early cosmos. Through this simulation, scientists can investigate phenomena that would be challenging to reach otherwise and research particles that existed in the early universe. Researchers can test theoretical predictions and improve particle physics models by simulating these severe conditions. The properties of hypothetical dark matter particles, for example, which are thought to account for a sizable amount of the universe's mass but are still difficult to directly detect, could be investigated by studies at the LHC. The deep ramifications of dark matter for our understanding of the cosmos motivate the search for its explanation. Although direct detection of dark matter is still difficult, it is now inferred from its gravitational effects on visible matter. By attempting to create dark matter particles in the lab, the LHC's experiments seek to solve this issue. If successful, this could lead to new discoveries and insights and transform our knowledge of the universe. These discoveries underscore the LHC's function as a scientific tool and a driving force behind groundbreaking discoveries that have the potential to transform our understanding of the world. One of the four fundamental forces in nature, the strong force, is another fascinating topic of study. Understanding the behavior of the strong force, which holds protons and neutrons together inside the atomic nucleus, at high energies can reveal information about the basic makeup of matter. Scientists may investigate the dynamics between quarks and gluons, the fundamental particles that mediate the strong force, thanks to the LHC's capacity to examine strong force interactions on an extreme scale. Deeper knowledge of nuclear physics and the processes influencing the behavior of atomic nuclei may result from these investigations. Beyond particle physics, the LHC is driving technology developments. Innovations in computing, data processing, and sensor technology have been sparked by the collider's intricate systems for detecting and analyzing particle collisions. For instance, the creation of the global web was first intended to facilitate the exchange of data from CERN's particle physics studies. These days, modern technology has completely changed how people communicate and share information worldwide. As an example of how significant scientific research may propel technology advancement, the LHC's requirements for computing and data management have had a wide-ranging impact on other industries. But using such a strong tool also necessitates strict safety regulations and moral considerations. Risks must be carefully evaluated because of the possibility of unforeseen consequences, like the production of novel or uncommon particles. The probability of catastrophic catastrophes cannot be completely ruled out, even though theoretical models indicate that their likelihood is exceedingly low. Because of this uncertainty, scientists must approach their job cautiously and openly, making sure that safety procedures are followed and that the public is aware of any possible hazards and the steps being taken to reduce them. Scientific research must include public participation and understanding, especially for programs that could have a significant impact on society as a whole. The LHC has attracted a lot of attention and conversation, underscoring the significance of making difficult scientific concepts understandable to a larger audience. Good science communication makes research easier to understand and encourages educated public discussion on the dangers and ramifications of cutting-edge scientific experiments. Researchers may resolve worries, clear up misunderstandings, and increase public confidence in the scientific method by keeping lines of communication open with the public. Important considerations concerning the direction of scientific research are brought up by the LHC's ongoing operation and the possibility of new discoveries. The capacity of the collider to investigate new facets of particle physics could raise fresh issues and problems, thereby expanding our understanding. To guarantee that research is carried out properly and that the advantages of scientific discoveries are maximized while reducing potential risks, scientists, engineers, and policymakers will need to work together continuously as they pursue new frontiers. The LHC is still a reminder of the inventiveness of people and their unwavering pursuit of knowledge. It represents the combined endeavor to unravel the deepest secrets of the cosmos by bringing together state-of-the-art technology, theoretical physics, and international cooperation. The ethical ramifications and possible repercussions of our discoveries must be kept in mind as we continue to investigate the fundamental forces and particles that form our universe. The Large Hadron Collider provides important insights into the nature of the universe and is, in some respects, at the forefront of scientific research. Its experiments could lead to the discovery of new fields of study, advanced technology, and change how we perceive the world. However, it carries a lot of responsibility along with its remarkable skills. To ensure that the search for understanding is in line with the larger ethical considerations of our day, the pursuit of knowledge must be balanced with a dedication to safety, transparency, and public participation. The scientific world as a whole believes that something fundamental has been found at CERN, with ramifications that go beyond what we currently know. Understanding the operation of the Large Hadron Collider is crucial before delving into the ramifications of Cox's assertion. The LHC, the most potent particle accelerator in the world, is a 17-mile ring of superconducting magnets constructed by CERN. Being able to replicate the circumstances of the universe's creation, it represents the height of human achievement. We are able to solve the universe's puzzles thanks to this incredible gadget, which reveals something genuinely revolutionary and possibly transformative. One of the most prominent research organizations in the world, CERN was founded in 1954 and has 23 member governments as well as a large scientific community. Although the LHC is CERN's main project, it is only a single component of a wider network of detectors and accelerators that study the subatomic realm. Protons are accelerated to almost the speed of light at the LHC, simulating the energy of the universe at the Big Bang. A sophisticated array of magnets guides the protons on their path, while sophisticated cooling mechanisms keep the magnets at temperatures lower than space. The subsequent collisions produce temperatures that are millions of times hotter than the sun's core. Operating underground and protected from cosmic radiation, the LHC is a wonder of engineering. For the superconducting magnets to work, the complete ring must be chilled to temperatures lower than the vacuum of space. ATLAS, CMS, ALICE, and LHCb are the four main particle detectors, and collisions happen at each of the four locations along the accelerator ring. By capturing the aftermath of collisions, these detectors enable researchers to sort through the debris in pursuit of the elusive Higgs boson, a particle essential to comprehending the structure of the cosmos. The LHC is a monument to human ingenuity and drive in addition to being a scientific instrument. It stands for our curiosity and our wish to comprehend the underlying processes forming the cosmos. However, we must also take into account the existential and moral issues that come up as we push the limits of our knowledge. What dangers come with venturing into the unknown? Could we unintentionally release forces beyond our control in our quest for greatness? In the sacred corridors of CERN, where the boundaries of human understanding are constantly being pushed, a revelation has surfaced that has chilled even the most seasoned scientists. A well-known figure in particle physics and former CERN researcher Brian Cox recently made a claim that shocked and worried conventional scientists. Replicating the Big Bang, the event that gave rise to our universe, in microcosm is the aim of CERN's Large Hadron Collider. Cox went on to discuss the possible consequences of this objective, pointing out that the LHC has the capacity to produce new phenomena, such as the discovery of the Higgs boson and the investigation of dark matter materials, which comprise a substantial amount of the universe. The prospect of simulating a tiny Big Bang at the LHC is not merely speculative. It is a real possibility. Scientists can witness the origin of existence itself because the conditions within the collider are identical to those that existed at the beginning of the cosmos. But such authority also carries a great deal of responsibility and possible danger. Take the scenario into consideration. What if something goes wrong? Russian physicist Anatoly Bugorsky suffered serious injuries in a 1978 accident at the Institute for High-Energy Physics in Russia when a malfunction led his head to collide with a proton beam. In spite of this, Bugorsky lived and carried on with his research, demonstrating the tremendous possibilities and risks associated with particle accelerators. One should not undervalue the dangers posed by a particle accelerator such as the LHC. Some members of the scientific community have legitimate concerns about the possibility of unforeseen consequences and the manipulation of reality itself. The potential for the LHC to produce microscopic black holes, areas of space-time with such a strong gravitational pull that not even light can escape, is a significant concern. In theory, the Earth could be consumed from the inside if the LHC were to create such a phenomena, even on a little scale. Scientists have reassured the public, nevertheless, that any black holes produced will quickly vanish. The basic principles of particle accelerator mechanics are necessary to comprehend how the LHC might produce a black hole. The energy of smashing protons together at almost the speed of light is so powerful that it has the potential to distort space-time itself. Imagine dropping a large object onto a stretched trampoline. The surface would bend and, if the weight were heavy enough, could make a hole. This illustration demonstrates how a gravitational anomaly could be produced by the LHC. Prominent physicists like the late Stephen Hawking have even expressed interest in this fascinating but unsettling possibility. Hawking warned that the Higgs boson might become unstable at very high energy levels, possibly leading to a catastrophic vacuum decay that could wipe out the universe. The well-known cosmologist Sir Martin Rees has also voiced worries about particle collider experiments, including those at CERN. In his book, Our Final Century, He examines the possible dangers of collider tests, such as the development of vacuum instability. Theoretically, this instability might cause a phase transition that would reverberate throughout space-time, resulting in an unthinkable catastrophe. Even if these situations are still purely speculative, even the slightest chance merits careful thought. There is very little room for error, and the stakes are extremely high. In order to reduce any possible risks, some researchers have carefully considered the risks that could arise from their studies and put in place comprehensive safety procedures and safeguards. Uncertainty is a natural aspect of scientific research, especially when exploring uncharted territory. There have always been risks involved in the quest for knowledge, but it is precisely this desire to push the envelope that has driven human progress. Although the LHC is the result of decades of scientific advancement and worldwide cooperation, beneath its magnificent exterior is a field of intense scientific investigation rife with possible risks and moral dilemmas. The elusive Higgs boson is one of the groundbreaking discoveries that have resulted from the collider's core goal of solving the riddles of particle physics. The massive energies produced inside its boundaries, however, also prompt worries about the potentially disastrous results of such an endeavor. Even while there are many safety precautions in place to reduce hazards, it is impossible to completely rule out the possibility of catastrophic occurrences like the formation of black holes or other unusual phenomena. It is essential to approach these studies with a keen awareness of the possible outcomes and a dedication to openness and public discussion as scientists continue to push the limits of our knowledge. The LHC is a monument to human ingenuity and the continuous effort to understand the underlying rules of the cosmos because of its unparalleled capabilities and potential for important discoveries. But beyond its motivational facade is a field of deep scientific investigation rife with dangers and moral dilemmas. The collider's experiments access forces and energy that are incomprehensible to the majority of the general public. Conditions similar to those of the early cosmos are created by the impact of subatomic particles traveling close to the speed of light.